Okay, so before we move on, just to recap, we have three major steps. All of this reconstruction that we saw so far has three major steps. First is your filtering, right? So you get your data acquisition as projections. That projection data has to be filtered. So we had filtered. The filtering can be accomplished in frequency domain or in time domain. So that came as filtered back projection or convolution back projection. But filtering is the first step after you collect the raw data, and then you have to do back projection. Finally, you have to submit. So these are the three major steps. So what is a raw data? It's a collection of projections, right? So we talked about how to view them. How did we view them? Oh, we could plot them as a sinogram, image of the projections as sinogram. So the raw data, what you get is the sinogram. This is the one that we saw before. And then when we did the reconstruction formally, when we built that material, we realized when you project this back by itself, you have a hazy picture, and that is not appropriate. So what we need to do is take a projection, apply filtering. So after you do that line by line, right, for every view angle, whatever projection you get, you do the filtering, you get a sinogram like this. Notice that it appears in the sinogram, it appears of poor contrast compared to the sinogram on the left. But this is not of our interest. This is not an image of interest for us. We don't want the blurring in the final image. So we are not really interested in making the sinogram look good. So this is a filtered version. The second step is, so for example, when we did this earlier, we said take a line and then we have to back project. So at every view angle, you have a projection. Now that projection is filtered, you have to back project in the field of view at the orientation, along the orientation in which it was acquired, right? So we took a particular angle. Remember, B30 is something that we showed as example before. So you take the projection along this line, right, and that one you project it back along the field of view at the angle. So this angle is the angle that you see here. Okay, so this is your back projection, but only same as back projection we saw before. Now we start with the filtered projections that you back project, and then finally summation. So you notice each of the back projection image itself is lousy, but when you start to add them, right, more the number you start to add, you get the final image, reconstructed image like this. Now you compare this image, right, you can go back, look at the notes. When we started, we gave this template image. We said, okay, what happens to this image? And look at the contrast when we got only when we did back projection, not filtering, right? This one is pretty damn close. This is like an object, right? This is fantastic. So how did this get? The more each one of the back projection itself contributed little bit, but then when you start to add all of that, you get a complete reconstruction, which is pretty damn good. So this is all it is. This is what we covered. Okay. So moving forward, this material is important that you actually try it. There is no, this is not going to be paper, and we can do some exercises, but then these are algorithms, and these algorithms you learn, understand more, visualize more when you implement it. So please take an effort to whatever way you have. Simple back projection of square, cube, right, which we did. You can try different geometries which are easy to get a feel for it. But if you have a real object, to project that, you cannot use paper and pencil and calculate, right? It will be tedious. So you cannot say, no, I don't have X-ray raw data and therefore I cannot work on it. That couldn't be an excuse here. Very famous image from image processing textbooks, examples that you will find, lena.jpg, right? This is a very commonly used example for image processing in classic textbooks. So what you can do, you can actually take this is a matrix, right? So what you can do is take this raw data, and then this is your image. You can create projections, right? You can write program in whichever language you have. You can write program to basically collect the projection sum along the line in each of the different orientations. So you can create your own sinogram for this, and you can play with this. How many projections can I use? What happens if I reduce the number of projections? What happens if I reduce the sampling along the L, right? If this is L, if you are going to project from top down like we did for the square example, this 250 is your L, number of elements. This is 0 degree. So if I have line projection, you add all this and you get one value here. Add all this, you get another value. So you get 250 array with 250 elements, and each value is sum along this 250, right? So you can do that. You can write program to create whichever projection angle you want. So you can create this sinogram and then see what happens if I be sparse, if I don't use certain view angles. What happens if I reduce the number of view angles? What happens if I reduce the number of projections, number of samples in the projections? All this you can try it on your own, right? So this is something that I encourage each of you to try on. It's actually very interesting, okay? So you can take any image and do it, okay? So we need to move on to say fan beam. So we will not do exact derivation like we did, we will not go step by step like we did for parallel ray projection. For fan beam, we exactly understand the instrumentation, right? We talked about the physics. So we know why when a fan beam is employed, and we now know the physics of, okay, the reconstruction is along the line you take and you back project. So here you back project and the back projections are all parallel. So what happens if it is a fan beam? It is not going to be parallel. So the only major difference is going to be how do we align our data, right? If we get that, rest of the equations you substitute back in the way we did the back projection algorithm for parallel ray, you have to modify that, okay? So we will not go too detailed in this because it will be an advanced topic if we really go into the detail, but just for completeness we will highlight how you have to modify, where you have to modify, and if you modify what happens. So fan beam reconstruction. So we can start out with first geometry, right? Because it is not parallel ray. First thing is this is fan. So when you say when it is fan beam, you have to know how to describe the geometry. So if you have a, so this is like your third generation system where your source and detector can move around, right? So this is a fan beam. Notice different configurations that are possible. You could have the spacing between the lines to be angle could be same, okay? Though that will, if that is the case, if this is line, then you may have unequal spacing here. Then you might say, no, I don't care about this, I want my L direction, I want evenly spaced detector. If that is happening, then maybe your angles will be different, okay? Or if this is not a line, if it is going to be a curve, then we have a better situation where I could have a constant angle and a constant spacing. So what we will do is we will take a simple case where it is okay, we have a constant angle, right, in this configuration like this. So we will start with this, and the reason where you can expect a change is this is the line. So we started out our reconstruction pretending this is the detector and it is summing everything along these lines, and then we had to back project and the geometry was parallel. Whereas here you have to back project along lines which probably can be described more in the angle or length depending on how you define the system, okay? So we will take this configuration. So if we take this configuration, is this sufficient for us to describe the geometry? Well, no. What do you have? You have a source, you have an object, you have a detector. So we have to have a reference frame so that you have a field of view where the object is placed, right, in relation to the data acquisition. One side is your source, the other side is your detector. So we will take ISO center in this configuration, that is where the patient is there. So that is your object near the ISO center. On one side you have your source, the other side you have your detector. So now how do I need to have some way to tell which is my view angle, right? This is going to rotate around the patient. So I need to know the view angle comes from where my source, this source, which angle is it, right? So, and then how far the distance is, how far is the source from this ISO center, how far the detector is from this ISO center, how far these lines are from the ISO center. So if we can define everything with respect to one coordinate system, then we may be able to quickly quickly integrate that, or look at our reconstruction algorithm for parallel ray and make appropriate changes in the geometry. So what we will do is, the fan beam reconstruction, we are going to call, so this is the source. So the source is going to move around the patient, so it is going to be at different angles, right? So that angle we will call at beta. But each beta you have a fan beam, the source is sending out fan beam. So the source can be at an angle beta, but within that fan beam you can refer to the angles as gamma, right? The lines that are going out in this fan, they can be at an angle gamma. So we can use this to describe the angle of the rays that are coming out. So likewise we could also use, right, this line can be referred to by your L. This is your theta, right? So we can refer to this line in L comma theta. Why do I want to do that? Oh, because we derived all our material using G of L comma theta. Okay, so here you notice G of L comma theta is fine, but everything was parallel. So only for a given view, only the L's were changing, whereas here for a given view, L is changing with respect to where you are on this line. Okay, so so we'll come to that. So then you have to place your sources, how much distance is it from this center. So that is capital D. Okay, so we can define this L, and this is an angle. We'll talk about this alpha. Alpha is nothing but this angle, right? What this perpendicular is making with respect to the vertical. Okay, so what we have is a source described by the angle and how far it is located from the isocenter. Usually this is fixed, right, because the gantry is there and the patient is sitting. So usually the D is fixed, but you can change your beta. Coverage can be increased or decreased depending on the beta. So to provide a complete view, what do you need? Oh, I need to be able to rotate around the patient. So I will have complete view I can get by beta taking 0 to 2 pi. So essentially what we are saying here is, if you are given a beta, right, if the source location is decided, the view angle is determined, then within that view angle each of the lines are determined by your gamma. So gamma specifies the detector position or the projection line. So this is defining that. So every time you take a data, your beta, right, your view angle could be different. So if that is changing, then the gamma is changing over some minus gamma m to plus gamma m, depending on the angles that you are taking. Okay, so in some sense your D beta, which defines your source, and for a given source the fan angle of the line, right, gamma, they completely specify the line projection. So if you tell me these three, we know exactly which line we are talking about. Okay, so from the geometry you can see that theta is nothing but beta plus gamma, and your L is d sine, your L is d sine of gamma. Your L is d sine gamma. Also notice that this is 90 degree and alpha plus theta is also 90 degree. So essentially using this geometry, if you go back, we can recognize that we had g of L comma theta representing the projections. Instead of g of L comma theta, now we can call, to avoid confusion, we can call it as projections at gamma comma beta. Beta is your, what was theta before, right, view angle. So here we are referring that to as beta. Your gamma, which was a line there, we didn't care about that. Now your gamma is specifying the line, which detector location. So you can use P of gamma comma beta to represent projection. So now you see, you have to maneuver this, and then it's the same filtered back projection that you are going to use. Only thing is, you now have a geometry where you have defined where you got the data, so you have to project it back along this geometry. That is the key. Okay. So before we, so we can do that, and you can do that for both filtered back projection and convolution back projection. Both you can derive, start from the equation, substitute these changes. Before we run on to do that, there is one more effect that we can see. I mean, one more coordinates that we can introduce. Why? Because you want to project it back, you will realize that it may be convenient because of the geometry. It may be convenient to represent a point in r comma theta rather than a line, right? Line was good when it was a parallel. So now maybe in this scheme of things, in the reference coordinates, a point can be better represented or better tracked down if we can write it in terms of r comma 5, some polar coordinates. Okay. So to do that, we kind of start to use a different variation from here, because you have to transform that. So we will now call this, right, d dashed, and then you have some 5 angle. So we want to relate everything in terms of d dashed and 5. We want to refer to this point in terms of d dashed and 5 instead of L and theta. Okay. Just for operational convenience. Okay. So you do this coordinate, you do this geometric transformation of the variables in your back projection. Some of the steps are actually given in the textbook. You might find the reference textbooks also have these derivations. Okay. Essentially substituting back into your formulation is there. So while you, so we are not going to derive that, that is little beyond the scope of what we want to cover at a introduction level. But if you were to go look at the textbook, at least the prints and links that I have picked from here, these are some of the typos that you may want to change. Okay, there is a dash missing or a square missing, or the variable is wrong. So this is a corrected version of it. But you have similar derivations in the other textbooks as well. Okay. So you start with your known back projection formulae, put this geometry so that the d, L, cos theta, all the terms were there, right? All that you have to change, theta should be changed, we have the relationships. So you substitute back, you will get a very similar looking back projection. So if you do this for convolution, for example, you will get the image in r comma 5 coordinates. So this is same 0 to 2 pi sum of, that means you are summing from all the views, right, all the views, that was theta, here it is beta. So no surprise there. What is this q gamma dashed beta? Oh, this is just a filtered. So here if you notice somewhere, you can see this is you have your projection, right, projection convolved with your filtered. That's what we did, even filtered back projection, convolution back projection. This is convolution. Only thing is, this is, instead of we called it g of L comma theta, now we are calling it as projection at gamma comma beta, because we changed the variables. And so this is your q of So this is your projection which is filtered. Okay. Only new thing is you have this term. What is this d dashed? Oh, d dashed we saw, which is the distance of the point from the source. Okay, in the previous slide we saw distance. So what this says is the convolution back projection for fan beam, slight difference has happened. Here you can think about it as, without this term it is filtered back projection, convolution filtered back projection, right? Convoluted filtering is implemented in convolution. So convolution back projection is what this is, same as what we did for parallel with geometry change. But in addition, if it is fan beam, this is a distance. D dashed is the distance of the point from the source. So essentially you have an inverse square. So there is a weighting based on the distance where the point is in the from the source. So you can think about this as weighted convolution back projection. So for fan beam, you can think that it's a back projection formula, that we convolution back projection of the parallel ray accounted for the geometry. After that you get this term. So you can think about this as a weighted convolution back projection. Okay, so I recommend you can actually read this material in from any of the textbooks. Only thing is the variables might be slightly different. Meaning of the variables will be analogous to how it is done here, but otherwise it's a very standard material. Like I said, again you will probably end up learning this better if you have access to data and you try to do the reconstruction by yourself. Okay. Okay, good. So let's move on. So this is our major topic of recon, which is beautiful material. I mean, I hope you appreciate. When we started, it was like we had this projection, how are we going to get the image, right? Without much, without flooding with theories or complex mathematics, intuition and common sense, we believed, got us to the back projection as an option. After that, the mathematical correctness gave us that, oh, there is a filtering term that should come. So it's actually, when they talk about recon, the basic recon algorithms are here. We have covered it. Starting here, you should be able to again expand it to cone beam. A popular FDK algorithm, if you search, you will look at it. Again, those are self-driven. We are not. It's a very introduction class where we cover several different modalities, so we will not go through that. But with the material that you have covered, if you understand this, you should be able to quickly get on top of things. So iterative reconstructions, what is that, right? So you can go start, if you understand what we have done so far, you should be able to quickly get on to the current state of the art. Okay, but within the scope of the syllabus here and the timing, we will not go. That is going to be self-driven. Okay, so image recon is done. Physics was done for X-ray modality first. Instrumentation for CT is done. Image reconstruction is done. What is the pending part for CT? Image quality. So now we need to talk about image quality. So when we talked about image quality, these are the things that we will cover. No surprises here. We will talk with resolution, noise. I mean, noise is not always talked in separation. It's the signal to noise or contrast to noise, and then some of the artifacts. Okay, so we'll quickly go to resolution. So what do we think is the problem in resolution? We are making an estimate, right? Your underlying ground truth is f of x comma y, but what you got is, using this recon algorithm and other things, you got an estimate of that f hat of x comma y is what you have got. So that's going to be a poor cousin of the ideal. So what happens to the resolution? Is it going to be same as the ground truth? No. What you are going to get is going to be as close as possible, or you want it to be as close as possible to the ground truth f of x comma y, but having said that, you still are only having estimate. So what are the aspects that are coming in? Oh, this is not ideal. We covered the reconstruction algorithm, but we kind of covered it from a theoretical aspect. But you have to implement, you notice that there is a filter, a filtered back projection. So there was a filter. you have to implement that filter. So we kind of alerted you that you cannot implement the ramp filter even though we just put filter as a ramp. You cannot implement directly that, and therefore you will kind of use a windowed function. So that means when you have a windowed function, that could introduce some spreading. And then we talked about all of the line integrals going to a point, right? Point detectors. Detector is not a point detector. It has an area. So what you are measuring at what you are saying that you got it at particular point is actually sum of all of the things that are falling on the detector surface, right? The area of the detector. So practical detector is not going to be infinitesimally small point. It is going to have some area, and so what you are getting is going to be good only over that area. There is a size effect. So what we can do is, we have done this before. All we are going to see, there is an ideal, and then because of these effects we can use these as, incorporate these as a convolution. Okay. So detector, it's not ideal detector, so it has a characterized by some indicator function S of L, right? Remember, impulse response of that detector. So we can have impulse response of the detector, and then you can have, this is your filter impulse response, right? Your filter function. So essentially you can think about your projection, the estimate that you have. So what we said is, what you are detecting, right? What you are measuring here is the projections. So you have an ideal projection, but because you are measuring this using a finite detector and doing a filtering, essentially you can think about your projections are an estimate of the ground truth projections. So you are estimating the projections, and the relationship between the real projection, what would be in ideal scenario which we use, and a practical scenario would be, your ideal one will be g of L comma theta. You have to convolve that with your impulse response of the detector, right? So this is not sufficient. So this you are going to apply another W. Okay. So recall, we had this estimate of the image. This is nothing but your filtered back projection. Okay, this is your filtered back projection. This is your estimated image. So what we have done is, we have incorporated the real effects. Oh, we ignored this before. Now we have introduced. There is a response of the detector. So detector's response function. Of course, this we said earlier. This ramp cannot be implemented, so you will have window function. So these two are incorporated in the equation. So now you look at this, you can start to look at it. Oh, you have an estimate. This is not ground. So f hat should be as close as possible to f of x comma y. Now we are going to think, oh, the f of f hat is not f of x comma y, because not because of the back projection algorithm, not because of back projection summation. It is because of this filtering, the detector and filtering. So your projection is an estimate, and that estimated projection is what is causing the blurring. Okay. So f hat can be thought as a reconstructed image from estimated projection. That's the key. So the back projection, the projection is not, we have been talking about back projection, right? But now we are saying, oh, it's not back projection. That projection, that of the data that you got, that projection itself is an estimate. So g of L comma theta was ideal, we said, when we developed the formulation. Now we say, oh, g of L comma theta itself, we actually have only g hat of L comma theta. We have only a measurement of that. We don't have the ground truth. And that is the one that we are using to back project and get the image. And therefore the estimate of image is affected by the starting point, which is your estimate of your projection. So now what is this, how is this affected? So let's see what is estimate, Fourier transform of your, right, this is in time domain or spatial domain, g of L comma theta. What is the Fourier transform of this? Oh, we saw that. So, Fourier transform is the ideal g of Fourier transform of the g of L comma theta frequency domain. So, multiplied with your detector response function and your window function, or in time domain, spatial domain, you can do as a convolution. So, this is the problem. So, this estimate, this is an estimate because of including these two effects. So, these two have an effect on the blurring, because that is a point spread functions that we have. So, because we start with the blurry projections, you have a blurry image. So, what determines the amount of blurriness? It better be something to do with the S and L, right. So, your G of L comma theta gets blurry because of this guy. This we can call as H tilde of L. This is the, in some sense, the blur caused by these two. So, if you really look at it, what is your G is the projection. So, your H is operating on G. G is G is one dimension. So, this is also applying in one dimension. But what is G? Oh, G is Radan transform. G is Radan transform, right? That is what we saw. Projection, you sum, you get G. So, it is actually a Radan transform of the, so it is a sum integral, right. So, in some sense, that means we will have to look at this as also, we are talking about this is a Radan transform. So, you collapse the 2 dimension to 1 dimension. So, what about this guy? So, you have a convolution here. So, let us just recall convolution property of Radan transform, very similar to your Fourier. So, Radan transform of a convolution of 2 function is Radan transform of each of the functions convolved. It turns out that this is the case, and therefore, looking at this in the previous equation that we just put, we can tease out that by comparing, we can tease out your H tilde of L that you saw is nothing but a Radan transform of H. So, that means, see, G is similar. What is G? Oh, you had a G of x comma y, right. So, that is projected, you get G of L comma theta, right. You collapse along the line. So, 2 dimension became 1 dimension. Similar thing here, that means your H tilde L is actually arrived from a 2 dimension H of x comma y, that is H of x comma y is the inverse Radan of this guy. Okay. So, fine, all we need is H of x comma y is your blur function in some sense, right. So, if you are looking at H of x y, it is the point spread function. So, this is how the ideal image f of x comma y is blurred by this function h of x comma y to get the estimate f hat of x comma y. Okay. So, f hat is the estimate, f of x comma y is the image, this is the image, this is the object, right, ideal. It is derated or it is blurred by this blurring function. What is this blurring function? This is nothing but h of x comma y, which is inverse Radan of this h of L. Okay, how do we compute this? Oh, we actually know something more about this h of L. What is that h of L? Oh, I know that this h of L, the Fourier transform of this h of L is what we wrote already, right. Fourier transform of that h of L is your detector function multiplied with window function. This is what you know about this. What is this? Oh, this is for applying the filter for every line of your projection, right. For every theta, your G of L comma theta, it is a collection. So, each of the 1D detector data, you are applying this, the detector has an effect and you are doing filtering, right. That is how you did it. And so, you did do this for every theta, same thing, and therefore, this is circularly symmetric. It turns out that this is circularly symmetric, the Fourier transform of this, right. If you arrange, it is circularly symmetric. So, when you have one-dimensional Fourier transform, one-dimensional relation, two-dimensional Fourier transform. We did talk about the relationship, and there was a transform that we said is useful. What was that? Especially in the circularly symmetric case, we said you could reduce the two dimension to one dimension, right? The frequency, now we can also talk about only the radius of the frequency, because theta is, it is circularly symmetric. The spatial domain, likewise, you can only talk about the r, the x and y, square root of x square plus y square is equal to r. So we could just talk about radius, because in the spatial domain also it's circularly symmetric. Did anything ring a bell? Yes, please go back. We talked about Hankel transform. So in order to calculate this guy, we could actually do Hankel transform, okay, because of this condition. So go look back at Hankel transform. So essentially we can use Hankel transform to get your h of r, your h of x comma y. Instead of that, you can get h of r, because it is circularly symmetric. So r is your square root of x square plus y square. So this is your blur function, okay. So you can calculate the blur function from your inverse Hankel transform. Clear? So fantastic. So resolution we talked about is always can be modeled as a blur function, and this is how the two practical constraints of what you are designing, right? What is your detector size and or detector response and your window function that you are operating. This is how that enters the blurring. Okay, so these are things that you could play with when you implement it, right? In any of the examples, like I said, Lena, right? You can take any image data, you can play with this blurring function. You can see what is the effect when you change the window size, window shape, Hamming, Sheplog, whatever detector function. You can give it some point spread value and see what's happening. Okay, good. So much for resolution. Then noise. So first we will cover noise, but then we will say noise is not treated in isolation. It has to be treated with respect to contrast, right, or the signal. Okay, so where is the noise coming from? So before we do that, what is our measurement? Our measurement is G of D. At the detector location you get, but we won't we won't play with this, because this is fine. We made one assumption, right? What is that? Oh, I don't want intensity. If I have monoenergetic, then I don't have to worry about intensity. I can essentially say we are operating at a equivalent energy, so that you have only one equivalent energy, monoenergetic case. So you have photons into energy per photon. So we will say instead of ID, if we treat a monoenergetic with the equivalent energy, then I can actually write this in terms of number of photons. Okay, so your GD instead of detector, now because we have I and J, why? Or because we have a collection, right? You have a collection from different lines, parallel lines. So I is your angle, J is your position. So you can essentially get Gij equal to minus ln of Nij by N naught. So much for what you have measured. But what you have measured, where is the noise coming from? Right, from the physics. Oh, we know Nij, the number of photons that are hitting the detector. Remember we talked about this. The burst, the time arrival could be statistical, and therefore we also said one of the random statistics that is useful, random variable useful, characterize this is your Poisson. So your randomness comes in your Nij, right? So randomness, when we say, then there is a statistics, mean and variance. Variance or the fluctuation is your noise, right? So where is the noise coming from? Noise is because of this guy, Nij, number of photons that are hitting the detector. Okay, so each time a burst is happening, each of the detectors probably are not getting the same number of photons because of that. So it actually comes out from a distribution called Poisson's. It forms a Poisson distribution, which we covered earlier, right? Why is this important? Oh, the mean and variance are same value. Okay, so what is mean? The variance is also the same value. That is the idea of this guy, Poisson. That is a characteristic of the Poisson random variable. So in our case, we can then say, okay, the randomness or the noise from n gets translated to the measurement noise, and therefore you have a mean of the measurement and a variance of the measurement, just because of your n, right? This is the random variable. So you have your mean. Okay, so this is your mean and variance. Okay, this is fine, but what are we really interested? We are not interested in mean and variance of the measured guy. We are interested in the mean and variance of the image, the noise in the image. Image is what we are going to characterize, right? Analyze. So where is this noise? How does this noise relate to the image that we want? Oh, you take this because this is the projection, and then you go to your reconstruction algorithm. So this goes into your reconstruction algorithm. How? So we will talk about, you are implementing a convolutional back projection, for example. So you start with some noise because of the G, and how does that affect your estimate? So this is your estimate. This is your, you are ending up doing what in CT? You are trying to get how the attenuation coefficient mu is distributed in space. That is what you are going after. So you get an estimate of that using some convolution back projection, right? So it is an approximate reconstruction, and therefore you are going to have, so you start with some noise and then you have some approximations because you are implementing it. So you get the noise in the image. So how do we get that? So if this is also right, because it's an approximate estimate, what goes in is a random variable. This is also going to have random fluctuations. So if we say random fluctuations, then we need to know, okay, so this is a random variable. If it is a random variable, how do I characterize that? I need to know the mean and variance. Okay. So we'll start with our formula, right? Back projection algorithm. So you have your mu of x. This is your formulation that we derived. Go look back, it's the same equation. You have your projection G of L comma theta. You have your filter function, right? C, and then dl d theta. Okay. So this is fine, but then this is ideal, right? So if you implement, you have to make some approximation. So you have to implement it. So you have to make discrete implementation of this. So what do you do? Oh, you'll have to first start about the approximations that you have to do. First is, when you say different view angles, you are going to have discrete number of view angles, right? So you are going to have, say, m angles you are going to take. That means your theta, delta theta is going to be pi over m. So that is your step angle. It's not continuous, right? You are going to stop, take, so number of views you are going to take is finite. So that is going to be one approximation. And then number of detector elements, right? Detector has a size, and therefore for a given width there can be only so many detectors, right? So your width of imaging or the detector length to the individual detector or the field of view length to the detector length, right? This is another. So if you have n plus 1 detectors, each of the detector you can say has a t width, for example. So that is a approximation, right? It has some finite width. So those two, and then if you do this, integrals become summation. Okay. So what we can have is an estimate. So this becomes an estimate, pi by m summation over t, right? T is your, and then your I. So, you can look at, right, this is your G, your filter function, everything now in discrete steps. Okay. So, this is your discrete convolution back projection. So, you have made an approximation. So, how does the noise random variable in this translate to the random variable here, or the randomness, the mean and variance in G, how does it translate to the mean and variance in mu? Because this is your image, the final image you are looking at is this distribution of mu of x comma y. So, what is the noise there, or what is the signal to noise ratio there? That will be of importance.